So the next talk we have is Kensuke Nunota from Osaka University toward the host star mass dependence of the planet frequency in the Roman era.
ありがとうございます。で、すみません。Okay, thank you for introducing. I'm Kansuke Nunota from Osaka University. Today I'm going to talking about the measurement of the host star mass dependence of the planet frequency. Here's the collaborator. Okay, this is introduction. Today, more than 5,000 planets have been discovered in a variety of methods. And the gravitational microlensing is one of the methods to detect exoplanets. The main purpose of the exoplanet survey is to perform the statistical analysis, and the measurement of the dependence of planet frequency is on the host star mass is one of the main objects of such statistical analysis, and it is crucial information for understanding the planet formation process. For inner planet, it has been well investigated by using the planetary sample from radial velocity. However, it has not been well investigated for outer planet, which can be discovered by the gravitational microlensing method. Because ground-based microlensing survey cannot measure the host star mass in most cases due to the degeneracy between the mass and distance. Roma is expected to discover more than 1,000 planets, and Roman can solve such kind of degeneracy between the mass and the distance by measuring the microlens flux or lens flux or something. So if we use a planetary sample with mass measurement, we can measure the host star mass dependence of planet frequency directly. But it is very difficult to avoid a statistical bias when using only sample with a measurement of the mass and distance. So it is very important to use all sample even without the mass measurement to solve to avoid such a statistical bias. And we developed the method that can measure the dependence of planet frequency on the host star mass ML and the distance from galactic center RL, even without the measurement of the ML and RL. In our analysis, we assume that the planet hosting probability is proportional to ML to the power of small m times RL to the power of small r. So a final goal of this method is to estimate this small m and small r value. Okay, next I will explain the detail of this method, and I will introduce the application for the planetary sample from ground-based microlens survey. Okay, in a ground-based microlens survey, we can measure the two types of parameter as information on the lens mass, lens system. The first one is the event time scale TE, and the second one is the lens source relative proper motion ML. TE can be written as a function of ML and RL, so that it has a strong relation with ML and RL. And ML is also strongly related with RL because, for example, when the RL is small, that means the system is in the galactic bulge, the ML becomes very fast. On the other hand, when the RL is big, large, that means the system is in the galactic disk, the ML will become very slow. So T and ML are strongly related with ML and RL, and to estimate the dependence of planetary frequency on ML and RL, we focus on the T and ML distribution. Okay, the principle of this method is very simple. If the planet frequency is dependent on the ML and RL, it means that if the small m and small r value is not zero, the ML and RL distribution will be different between the planetary system and a single system. because T and mu L is strongly related with ML and RL, if there is a difference between of the ML and RL between the planetary system and single system, T and mu L distribution should also be different. So by comparing the T and mu L distribution of the planetary system with single system, we can estimate the small m and small r value. Okay, to test this method, we apply this method to a sample from ground-based microlensing survey. In our analysis, we compare the mu distribution of planetary events from MOA2 ground-based microlensing survey with single events from a galactic model. Our planetary event consists of 22 planets from MOA2 survey, and we use a Cosmos galactic model from Cosmos et al. 2021 as a galactic model. By using the galactic model, we can make the distribution of the single microlensing event. So by resampling this sample weighted by the planet hosting probability in the value of specific value of M and R, we can make the planetary sample of the planetary event in the assume of specific value of small m and small r value. This right figure show. Okay, look at this right figure. This black dot shows T and mu distribution of planetary events from MOA2 survey, and color map shows the model predicted distribution under the assumption of m equals 0 and r equals 0. And this figure is almost same here, but the color map shows the model predicted distribution under the assumption of m equals 0.4 and r equals 0.2. So by comparing these two distributions, we can notice that the assumption of m equals 0.4 and r equals 0.2 is much better than the previous assumption. So by evaluating this degree of match of these two distributions, we can evaluate the small m and smaller value. To calculate this degree of match, we calculate the likelihood by using this equation. And this is a result of our analysis. This color map shows the likelihood distribution of small m and small r. The median value is m equals 0.5 and r equals 0.1. The uncertainty is very large, but we can notice that this distribution prefers m larger than 0. If this result is correct, it suggests that the massive host star more likely has more planets. Yeah, so it is very interesting result. And we also perform the same analysis by using the subsample divided by their mass ratio. The left panel shows the result of subsample with mass ratio 10 to smaller than 10 to the minus 3, and right panel shows the result of subsample with mass ratio larger than 10 to the minus 3. So in this figure, we can notice that in the left panel, the likelihood distribution is prefers m equals 0, and the distribution in the right panel is prefers m larger than 0. And this is more clear figure. This shows a likelihood, one-dimensional likelihood distribution of small m. So it also has large uncertainty, but if this result is correct, this result suggests that a massive planet is more likely to exist around more massive star, and lower mass planets commonly exist regardless of the host star mass. Yeah, so this is also a very interesting result, but the uncertainty is still very large. Okay. So to reduce this uncertainty, we need more sample. And as I mentioned, Roma is expected to discover more than 1,000 planets. To estimate the effect of the Roman sample. Roman sample, we performed mock data analysis at various number of planets. And this right figure shows one-dimensional distribution of small m value in the various number of the planets. And this figure shows the relationship between the number of planets versus uncertainty. We can estimate that the uncertainty will be reduced to around 30% if we use the 2000 planet sample. But this mock simulation is in this mock simulation, we only use T and mu rel, but the Roman can measure lens flux or microlensing parallax in a majority of the case. So by adding this constraint of the lens flux and parallax, we can make a much stronger constraint. So we can settle on whether this interesting result is correct or not by using the Roman sample from Roma. This is the final result. This is summary. Ground-based microlensing survey suggests that massive planets are more likely to exist around a massive star, and lower mass planets exist regardless of the host star mass. And by using Roman sample, we can settle on whether this result is correct or not. This is that's it. Thank you.
Thank you. For finishing a minute earlier and bringing us a little bit closer to the coffee break. So, does anyone have any questions in the room or online? And are we getting a laptop plugged in?
Hi, I might have just missed this, but maybe this is just a clarification question. So when you say lower mass planets exist regardless of the host star mass, like, do you mean it's a less dependence, or do you mean there's like no dependence? And I ask because like for transit, there definitely is a dependence.
So what do you mean this result?
Yeah.
Sorry, one more, please.
Oh, yeah. So I'm just asking, so when you say the lower mass planets are common regardless of the host star mass, I guess what I'm asking is like, what is the range of host star mass that you're talking about? And is there any sort of dependence, or is there no statistical dependence?
Sorry, are you mentioning the left figure? Sorry.
Maybe it's better if we discuss offline.
Okay.
Okay.
Sorry.
So yeah, we got time for one more question. There's one at the back.
I'm sorry, it's not clear to me why you expect there to be two distributions and not just some sequence, just some continuum, as it were. Sorry, I'm not sure. I'm not quite understanding why you expect there to be two distributions and not a continuum in your two plots, as it were. Yeah,
This one?
the other plot. Go back. Back.
Okay.
Yeah.
Yeah.
Why you don't expect there just to be a continuum?
The question is why are you separating the sample and don't you expect it to be a continuous chain?
This continuous change?
Is there a reason why you chose to separate it into two samples of high mass and low mass? Consider a continuous
because the number of sample is very small. So maybe we analyze the continuous tab. Maybe I think that the uncertainty is very large, so we cannot such analysis, I think.
Okay, thank you.
Sorry.
Thank you.